Now let's do change of basis. Now first I would like to tell you one thing, that choice of any basis is completely arbitrary. I may choose one basis, but you may choose another basis, but the physics remains same. Whatever basis I choose, if I want to evaluate a particular variable on it, suppose I want to find out energy on my basis, and you also want to find out energy on your basis, two results must be same, because nature has already calculated the energy value. So whatever may be our mathematical choice, that value remains the same. So I have already this basis. With this basis EIAK we are familiar with. For n-dimensional complex vector space, I runs from 1 to n, and any vector A can be written as a linear combination of these basis vectors as they are complete, and AI are corresponding components of this kth vector A, and all these AI are actually complex number. In terms of matrix, this kth vector is a column matrix, a bra vector is a row matrix, and we have already calculated this, that the component AI in the basis EI can be obtained by doing the scalar product of EI and the vector A itself. Now in AI basis, if I make this kth vector to a bra vector, the column matrix become row matrix, and as we are dealing with a complex space, so all these individual elements, each element will be complex conjugate of this A kth vector. And this is how we defined O. O is an operator which may be written like this, which is a n by n matrix with n square number of elements, and this is specified in this basis, because we have already written the any element OIK of this operator O in basis EI, which looks like this. This is actually element of OIK, so O, element of O, so it is OIK equal to this much. We have already used this. Now suppose I make a change of basis. Suppose my new basis is called F alpha ket. It would be F alpha, F beta, and as EI, EK satisfy the orthonormality condition, these basis vectors are also satisfies the orthonormality condition. That is the property of basis vectors. The basis vectors should be complete, otherwise I cannot write any vector like I wrote here. I cannot write any vector as linear combination of these basis vectors. So this is my orthonormality property, this is my completeness, which tells me that this outer product of these two basis vectors F alpha and F alpha, if it is written like this, then it is called outer product, and if the scalar product is written like this is called inner product. Now in this F basis, my kth vector is written as A1 tilde, A2 tilde up to AN tilde. This tilde sign is just to tell you that we are now in F basis. So as we have done earlier, for AI we wrote that AI equal to EI base vector A, which is in the basis EI. So for F basis we can write it similarly, any component A alpha tilde like this, and completeness will give me that any vector A can be written as a linear combination of these basis vectors with this complex components are there. A, alpha, tilde are the complex numbers. These are components of this kth vector A. And the bra vector is also written like this. So in F basis, the components of the operator will look like this: O11 tilde, O(n1) tilde, etc. And the nth matrix element is ONN tilde. This one. As we have written in EI-EK basis, the ikth component of the operator O is like this: OIK equal to EI O operator and EK kth vector. Similarly, for F basis, alpha beta element of the operator O can be written like this. This operator O is now sandwiched between these two basis vectors. Now we are in the F basis. Now what if we want to make a transformation from EI to F alpha basis, or simply E to F basis? Now from the definition of component of the kth vector A in F basis, we can write A alpha tilde equal to F alpha A. This is from definition. I can put this identity operator here, no harm in that. An identity operator in EI basis or in E basis looks like this. So I can take this summation out. So what I am left with, the scalar product of F alpha and EI and the scalar product of EI and A. According to the definition of the component of the kth vector A in EI basis, I can write this particular scalar product, this particular inner product as AI, and I am left with F alpha EI. So this is basically a scalar product of both bases. One is F basis, other is E basis, and we define this quantity as U alpha I. That means if I consider this U as a matrix, then one component is from F basis, other component is from E basis. So U alpha I is another matrix but with n square element, n elements from E basis and other n elements are from F basis. And if we apply this matrix U alpha I to this AI, I will get A alpha tilde. That means here I am switching from E basis to F basis. In matrix notation, this can be written like this. Let's discuss about the nature of the matrix U, which helps us to transform from one basis to the other, say from E basis to the F. We need to prove that U dagger U equal to identity matrix if U is an unitary matrix. This identity matrix obviously contains n square components, so it is also n by n matrix, because U is a n by n matrix and U dagger is obviously another n by n matrix. So this is the condition of unitary matrix. The proof is, I am starting with U dagger U, which is another matrix, because this is a simple multiplication. This is n by n matrix, this is another n by n matrix. So U dagger U gives me another matrix, and I am now concerned about the ijth element of that product matrix. So whenever I am putting this alpha, and now I am U actually contains elements from both bases. It also contains elements from F basis and E basis. So we can write like this, where alpha goes from 1 to n, and in place of U dagger I alpha, I can write it as U alpha I complex conjugate of this. These two things are similar. And U alpha I is nothing but F alpha EI. The complex conjugation sign is already there, and U alpha J is there, summation over alpha. And in place of U alpha J, similarly we can write F alpha EJ. So in the next step, it is EI F alpha, that is scalar product of EI F alpha and the scalar product of F alpha EJ. If I can remember the completeness relation, where it was stated that I can write the two basis vectors like this with a summation over the indices, and that will give me this identity matrix I. So identity means 1, so I am left with EI EJ, which from the orthonormality of EI AJ is delta IJ, and if I equal to J, this turns out to be 1, that is identity. So here we have proved that U is an identity matrix.